So let's talk a little bit about focal spot size again. Again, the focal spot size idea is going to become very important when we need to start talking about image quality, right? How we produce quality images, or what are the qualities of the images we produce. One of them is going to be detail or sharpness. Okay, and the focal spot size, among other things, but the focal spot size directly affects image detail, right? Everything else you do can, lots of other things you do can affect image detail, but this one is sort of the starting point for the effects on image detail. When possible, you want to be using the smaller sized focal spot. You accessing the small filament, small focal spot. But when the small focal spot is selected, and you try to access high milliamperage settings, like is required for larger body parts, or if we talked about MAS before, mass, right? Milliamperage seconds. If you try to access high mass settings with short exposure times, you'll be forced onto the high MA stations, okay? When you're forced to use the high MA stations, usually 200 or above 200, as they say here, you are locked out. You are prevented from accessing the small focal spot. Okay, so the settings that you make on the console will kind of control if you can get to the small focal spot or not. And this is again done with circuitry to protect the equipment. So sometimes you can access the small focal spot. Like on our equipment, you can access small focal spot no matter what the exposure time or KVP is, but as long as your MA is 150, 100, or 50. Right, you only have 3 MA stations where you can access the small, I think it's, yeah, that might be right. But either way, you only have 3 MA stations or so where you can access the small focal spot. Other equipment might let you get to the small focal spot at higher MA stations, but as soon as you raise the KVP high enough, it may prevent you. But in any case, the moral of the story is that you may be locked out, prevented from accessing the smaller sized focal spot to prevent excessive heat load being concentrated onto too small of an area on the anode disc and potentially damaging the anode disc. Hopefully when you guys have this in your hand, you saw all the cracks in it, right? One of those cracks actually runs through all the way to the back of the anode disc. Okay, crack the whole disc down the center. This disc has failed now, right? This is why this was removed from an X-ray room. The disc had failed. Okay. On top of that, there's going to be an effect of it's going to seem kind of odd to say, but what are the 3 states of matter that we know about? Like matter can be in one of these 3 states: solid, gas, or liquid, or in the order that they kind of go in: solid, liquid, gas, right? Like an ice cube, right? An ice cube is frozen water, right? It's the solid form of water. Water can be heated up and turned into a liquid. If you heat water up high enough, hot enough, it turns into steam. That's the gas, right? Well, what form is the tungsten of the anode disc in right now? It's a solid, right? Well, it has a melting point where it will turn into a liquid, 3,400 degrees Celsius, right? There is an additionally higher point, a higher phase transition when it gets hotter, and it can turn into a gas. Okay, metals can be gases just like any other materials, right? If you heat them up hot enough, they can turn into a gas just like anything else. It's just that you have to heat them up really, really hot to turn them into a gas, right? Well, you can produce enough heat inside of the equipment to vaporize tungsten, and here's the problem. When you turn something into a vapor, a gas, it sort of wants to spread around everywhere, right? But what's surrounding this whole setup? The glass, right? So now there's going to be a limit to how far that gas can spread, and that gas can now spread onto the glass, depositing metal onto the glass. And we're going to learn in a little bit that has some major problems for the equipment over time. So we want to prevent too much heat being applied to the anode face too quickly, or into too small of an area. And so, yeah, the circuitry sort of prevents you from doing things that are overtly damaging to the equipment. The fortunate thing is most body parts that require maximum sharpness detail are small. So we don't need to use high energy, high exposures, high kV, high mass numbers. They usually don't require MA settings above 200, and we can use lower KVP settings: fingers, hands, wrists, forearms, feet, toes, ankles, all that stuff. Okay, facial bones, right? So small body parts, smaller, more detailed body parts use smaller, require smaller exposures, and we can use the small MA, low MA settings, small focal spots. You should be mindful to select the small focal spot when possible to maximize image sharpness for smaller body parts. Here's what I'd like you guys to do if you're in a clinical setting. Next time you're in your clinic, ask the precepting X-ray tech about focal spots and see what they have to say about them. Right? They might go, "What's a focal spot?" Right? Because they have been out of school for 20 years or something, right? But they also might say, "Oh yeah, I access the small focal spot with low MA settings when I'm doing like hands and wrists and stuff like that." It might be just that they just haven't talked to you about it. But I'm going to ask you guys to go out and talk to them, see what they have to say about this, right? I have an opinion that you should be using it when you can use it to achieve better image detail.
Where do you find it on, like,
Yeah, so
if it's digital?
So if it's digital, right on the console, there should be a setting for small or large focal spot. You can just actually switch between small and large. Some equipment, it's set by the milliamperage station. So you change the milliamperage station and its focal spot is brought from small up to small or large. So you have to see, and this is what you'll want to ask the X-ray tech specific for your equipment.
Well, I've done it for 22 years and I've never heard of it, so that's why I was like.
Yeah, so it should be right there on the focal spot, right there on the control console, an option to switch between small and large. When you get to start at MedStop, you'll see on ours we can switch between small and large. On the one we use here at the school, it's MA dependent. The MA station sets your focal spot size, and that's what the S or the L you'll see next to the MA number. But definitely ask people that you've been working with to show you that, and they can show you how to adjust that. They probably, if they're setting, is anybody setting their own technical factors in the clinical setting right now? You are? So others, are you getting it set for you? No? So you're setting it yourselves? Okay. So start to look for this, okay? If you're not...
It's on the dial, right?
It should be.
Yeah.
It's super equipment dependent. Like it depends on what kind of console you
Because
have.
I've seen it and I asked, but she just really didn't know what it
Gotcha.
Yeah.
So it's time to get some education going, right? You help them out. But yeah, now you guys know what it's used for. It's used to change image detail, or large focal spots used to achieve high MAS numbers, high mass numbers. And this gives us a little extra heat capacity on the equipment and to get to those high numbers without damaging things. Okay, awesome. The next things to learn about the focal spot, we're going to learn a few more things about focal spot, and then we do it again in the next module, not next class, but all the way in the next module, a ways away. The nominal focal spot is the size of the focal spot. That's nominal or normal. It's what the focal spot should be normally. It's what the advertised size of the focal spot is on the specs sheet, and this can be slightly different because it's not a light bulb, right? It's a spot that you're directing an electron beam at, and there can be some variance in the actual electron beam that's shot towards the anode, variance in the size of the area that it hits versus what the manufacturer actually puts on their spec sheet. So I guess it is said that the actual focal spot can be about 50% larger than the advertised size, but these small differences don't make a big difference. This is because of the mutual repulsion of the electrons. Okay, so the manufacturers do their little calculations to determine the size of the focal spot, put that on the spec sheet, but the focal spot, as they say here, using quotations, blooms. It gets a little larger than it's actually advertised to be. The electrons repel each other. The actual focal spot swells up in size, especially at higher milliamperage stations, because remember, milliamperage is tube current, is the amount of electrons in the beam, right? Higher MA stations, more electrons in the beam, more mutual repulsion between those electrons, and so you get larger and larger focal spots. Even if you're on the small focal spot setting on the small filament, as you increase your milliamperage, the focal spot effectively will get larger and larger at higher MA stations. Bless you. Bless you twice. The actual shape of the focal spot takes the shape of a kind of a butterfly wings, or they call it a swollen letter H. Looks like butterfly wings to me. And we give the dimension, like we said, the 1 by 1 millimeter large size or 0.5 millimeter by 0.5 millimeter small size. We get those dimensions by treating that as a roughly just a square or rectangle, as a square object. Okay, awesome. So circling back around now to the anode disc, right? It's going to be a lot of focus on the focal spot because this is where the X-rays are coming from, right? So focusing back on the anode disc, we talked about that the anode disc was cut at an angle. We say that the anode is beveled. Beveled means to make an angled cut. You guys have learned the term bevel in medical assisting, right? When you talk about the needle, right, the angled cut at the end of the needle to make the needle pointy. Well, the anode disc is beveled. It's angled. It's cut. And that's important because we want the X-ray beam to be directed downward, okay, not back at the cathode. So here's the idea. There's an electron beam traveling from cathode towards anode. It has a width, okay? That electron beam strikes what is called the actual focal spot, okay? That is the width of the area that's struck by the electrons. But if you were to stand underneath the X-ray tube like this, that area that is actually, yay wide, looks narrower to you from up underneath, okay? This is referred to as the effective focal spot. So the actual focal spot as projected downward towards the tabletop, or wall or whatever, projected downward towards the tabletop, is going to be narrower than the actual focal spot. So the effective or useful focal spot, what actually produces the image sharpness, is narrower than the actual focal spot is. This is an idea called the line focus principle. It's not going to be given here, I don't think, as that term is not going to be given out here, but just kind of put that term in the back of your mind, remember it. A couple of months from now, we'll get into that a little bit more. The line focus principle. It's the size of the focal spot as seen by the image receptor. So you're laying on the table looking up at the X-ray tube. How big does the focal spot appear to you, right? Like this pen has a width. If I hold it like that, there's the width of the pen. But if I turn this pen, it doesn't look quite as long, And here's the other thing, right? Over on this side of the room, over there, right? The pen looks very small to you. It's very narrow because I'm pointing the pen directly at you, right? But where Emily's sitting, the pen looks a little wider because you have a different angle on the pen, right? As we move this way through the room, you all have a different view on this pen, and the apparent width of the pen changes depending on where you're sitting in this room, right? It's only when I turn the pen like that you notice that the pen has a longer width than was apparent to you. The effective focal spot is like turning this pen in relationship to where you're sitting. Right? Okay, that's going to become important later down the line, but this effective focal spot is due to the beveled or sloped surface of the anode at the focal track. The effective focal spot is much smaller than the actual, which is defined, the actual spot is the area defined as being struck by the electrons. This will have something to do with image quality as we go forward. You could also imagine that as that anode bevel, if the angle were to change on the anode bevel, that would change the size of the effective focal spot. Yeah? If this anode bevel were to be brought back to 45 degrees, then the actual focal spot, the width of the electron beam and the effective focal spot would be at the same size. Okay? And as it's brought closer to perpendicular to the beam, the effective focal spot would narrow. Okay, it's like the view you guys had on my pen. You're looking straight on at my pen versus you guys over here who see more of the width of the pen. Okay, so by changing the anode bevel, that would change the size of the effective focal spot. Now we don't change the size of the anode bevel, but different X-ray tubes would have different anode bevel angles depending on their use. Okay, that's something we'll circle back around to in the future. Let's talk about the glass envelope. So we've done a lot about the internal components, cathode, anode. Now the envelope that holds it all together. All components of the X-ray tube are encased within a glass envelope containing a vacuum. What it means to contain a vacuum is it means that all air molecules or gases of any kind have been removed from the inside of the glass. Okay, the thing has been sucked free of all the atmosphere. Okay, there's no atmosphere inside of the tube. There's nothing to run into. Any air molecules or other gases would impede the flow of projectile electrons because they would just run into them. The electrons would just start to run into air molecules. Okay, so if for some reason the X-ray tube lost its vacuum, radiographic techniques, the settings that you make would become wildly unpredictable. Plus, in the real world, the glass would be cracked and the oil would leak into the tube, and that'd be a separate problem. But effectively, if the vacuum is lost, then you can't set technique anymore. The glass envelope is made of Pyrex glass. We use Pyrex in our dishware, right? Our like baking ware and stuff like that. It makes it so like they can, we can stick it in the oven at 500 degrees, right? And then it can also like not crack when we take it out of the oven and cool it down, right? If you've ever taken a piece of glass, like a glass cooking pan or something, put it in the oven and then accidentally put it in the sink and run water on it when it was still hot, I have. What happens to it? It shatters, right? Because the glass expands as it heats up, and then as soon as you run cool water on it, it cools and contracts, and different areas will cool quicker than the others, and put stresses on the glass, and the glass just shatters when that happens. Pyrex is much more resistant to that happening than just like a regular old glass pan. So strong Pyrex glass is used to form an airtight seal because it's resilient to extreme heat generated during X-ray exposure. That glass envelope gets very thin at the window. We showed that earlier. That's right underneath the cathode anode spot. And this is the area that the X-ray beam is directed through, which the effective focal spot is directed toward.